Okay, what's our strategy if we're trying to take a limit of something like that? What form is that? If I try to evaluate this directly, everybody see that that's the form 1 to the infinity, right? The limit of the base is 1 and the limit of the exponent would be positive infinity. I'm approaching 0 from the right, okay? So what do we do with that? It's a function of the form f of x to the g of x. So what's our strategy for simplifying a limit like this? And this is just, this is this is above the AP level stuff. AP doesn't cover this, but I think you should see this before you go to college. Remember what we did? Okay, this is the stuff, it's that stuff, right? Remember this? So it's just, you got to just think in terms of, if I were going to differentiate, I would have to use logarithmic differentiation here, right? If I have a function to a function, that's when I use logarithmic differentiation. I'm going to use a similar strategy for resolving this limit. Okay, step 1 is we're just going to let this thing equal y. Okay, we're going to let this function equal y, right? So whatever the function is that we're taking a limit of, set y equal to that, okay? All right, so okay, now what? Okay, we log both sides. Yeah, we log both sides. So step 2, log y equals, how would this side simplify if I take the log? Okay, yeah, the log of a function to an exponent. Remember, I can bring the exponent out in front of the log. So we'd get 1 over x log of 1 plus x. Okay, now what form does that have? If we were going to take the limit here, right? So look what we did. Okay. We got to here. Step 1, we logged both sides. Now we're going to take the limit, right, as x approaches 0 plus in our case. Right, and I guess they call this, here, I'll tell you what, they call this all step 1. We'll follow that recipe, that's fine. So now, okay, what's that look like? Oops, log, sorry. Forgot the log, didn't I? Yeah, I was about to say, that didn't look right. So what's that going to give us? What form is that going to be? 1 over x as x approaches 0 plus is what? Infinity times, what's the log of 1 plus 0 plus? So the log of 1 point something. Yeah, think in terms of a graph. Always just think in terms of that graph, right? What are the coordinates of that point on the graph? 1, 0. So what's the limit of the log of 1 point something? Looks like I'm going to get a slightly positive number for my output if I input 0, or I'm sorry, 1 point something. Did I say 0 point something? If I input like a 1 point something, I'm going to be kind of right up there, right? So I'm going to get 0 plus, right? So it looks like infinity times 0. Now we know how to deal with that. Oh, darn it. What's our strategy for infinity times 0? Okay, we got to write it as a fraction, right? We got to write it as a fraction where it's going to be an indeterminate fraction, either infinity over infinity or 0 over 0, whichever one seems to be the most convenient. Both of those, though, are the cases where we can use L'Hopital's rule, right? If we go back, and let's just do a 10-second review here. If we go back all the way to L'Hopital's rule, I guess that's where we stopped the other day, but this is a good example, right? Here's one where we ended up with infinity over infinity, right? So all we had to do was differentiate the top and the bottom separately until it's no longer indeterminate, right? Okay, so that's no big deal. Once we get down to a ratio 0 over 0 or infinity over infinity, we're good. Then we can just crank out L'Hopital's rule and not a big deal. Okay, so which way would be better here? I want to write this as a ratio, as a fraction. Yeah, we want to put the log on top because then on the bottom, I get 1 over x, which is just x, right? Okay, so we're going to write this as the limit of log y is equal to the limit of log 1 plus x over x as x approaches 0 from the right. Well, that just looks like 0 over 0, right? Okay. So what would we do to the right side? What am I going to do here? Pagan, what am I going to do here if I've got the form 0 over 0? Take derivative top, derivative of the bottom separately. Good. So this is equal to the limit of bottom's just going to be 1, isn't it? The top, what's the derivative of log of 1 plus x? Yeah, 1 over 1 plus x, right? The derivative of log u is just u prime over u, right? Well, u prime in this case is just 1. So I get that, don't I? That's what we get on the top. Well, that's just equal to the log of 1 over 1 plus x as x approaches 0. What's that equal to? What's the derivative of I mean, sorry, what's the limit of 1 over 1 plus x as x goes to 0? 1 over 1, which is 1, isn't it? Okay, aha. So now we know that the limit of log y is equal to 1. Now what do we do? Because we got the limit of log y. We want the limit of y, right? That was the original problem, was the limit of this guy right here, which we defined as y. So how am I gonna get that? Say it again. Okay, I'm gonna exponentiate both sides, right? And there's the last step. Okay, we found the limit of log y, and now we know that if the limit of log y equals L, that's our limit. Ours was 1, right? It's going to be a number. then the limit of y is going to equal e to the L, right? I'm just going to exponentiate both sides, okay? Does that give me 1 to 5 on that last step? Does that make sense? Okay, if that one's not making 100%, somebody see if you can formulate a question. What about that is not clear? What can I clarify? Yep.
I think it's just the previous step. I think I get the idea. Well, I get the idea of like how we can get just y by itself to get the limit of y equals to an answer or whatever. But it's just the before part.
This step 2.
Yes.
Is that where people are? Right. So is that true? Give me, how many people are where is it you feel stuck here on 1, 2, or 3? Show me fingers here. Step 1, step 2, step 3. Step 2. Okay, if you're feeling stuck at all, Becca, what's the part you feel least comfortable with? Step 2. Okay, so step 2, let's review what we did in step 2. Step 2 is where we unlocked this weird function by taking the log of both sides, right? Because we had this function that was 1 plus x to the power 1 over x, right? Function to a function is tough to deal with. That doesn't match anything remotely, like it's indeterminate and it doesn't match L'Hopital's rule, right? Our goal here is always, we've got to get this thing somehow, we've got to manipulate this to get it into the ratio form 0 over 0 or infinity over infinity. We have to do that to use L'Hopital's rule, because L'Hopital's rule depends on that, right? L'Hopital's rule is exclusively for evaluating limits with indeterminate forms 0 over 0 or infinity over infinity. That's it. It's limited to that, right? Okay.
How were you able to put on the second line for number 2?
Okay.
How were you able to put everything over x?
Oh, okay. Over here, how was I able to put everything over x? Well, because here's how. Because there's our infinity, there's our 0, right? Well, I'm going to write this as the log part divided by the reciprocal of this one, right? Because wouldn't you agree in general, this is true? If I have a times b, isn't that equal to b divided by the reciprocal of a? Okay, see how that works? Okay, yep. You could, which is the very same thing, just multiplying straight across. Yeah, either way, we're going to get that out of it. Okay, and once we get to there, now it matches. Look, that's what we needed. Okay, it matches. Now it's in a ratio form, 0 over 0, so we can just use L'Hopital's rule. Okay, so then, does that clear that up a little bit? Okay, so then how about going from step 2 to step 3? Does that make sense to everybody? Okay. They're skipping a property of logs here. They're saying that we have this property of logs that says says this. We don't need to get too mired down in the details here, but if limit of f of x equals L, then we could say this: the limit of a to the f of x equals a to the limit of f of x equals a to the L. Okay? That makes sense? That's a property of limits that we just have, that we can use. Okay? So that's what allows us to go from there down to there. Okay, we can exponentiate. Say it again.
Can you just go back down to that property?
Okay. Okay, so we can do that here, right? We could say then the next step would be whoops, supposed to be a log y. Darn it, when I write limit, I don't know, it just seems somehow redundant to write limit of log. They both start with L, I guess. I don't know what I'm doing. Right? Okay, and then by definition, whoops, e to the right? If I exponentiate a log function, they cancel. There's an intermediate step there. I'm really doing this, but I'm not showing this step. We don't have to, but what that really means, that's equivalent to the limit of e to the log y. And so that undoes the log, right? And we end up with y is equal to e. Okay? And what's y? Well, y is our answer. We called this whole thing y. So that's our answer. That limit is equal to e. Okay? Those are tricky. They're tricky. Okay, and then here's quick summary of the strategies then, right? So indeterminate forms. If we have 0 over 0 or infinity over infinity, the strategy is just L'Hopital's rule, very straightforward, okay? If we have 0 times infinity or infinity minus infinity, those are the situations where we've got two steps. We've got to convert that to the form 0 over 0 or infinity over infinity, then use L'Hopital's rule. If we've got one of these bizarre, f of x to g of x forms, so those would be the indeterminate forms, either 1 to the infinity, 0 to the 0, or infinity to the 0. When you try to directly evaluate if it looks like one of those three forms, that's where we're going to use this log trick. You log both sides, set it equal to y, set the function equal to y, log both sides. You apply limits of logs to simplify that. You find the limit of log y using the above strategies, right? Whatever that requires, you're going to eventually have to get that into a ratio form and simplify using L'Hopital's rule. And then finally, you just use the fact that the limit of log y, if the limit of log y is L, then the limit of y is e to the L. And we're done. Okay, these are not indeterminate. Those are determinant forms, and you would be inappropriate. You're done. If you see those, 0 minus 0 is equal to 0. That's not indeterminate. If your limit looks like that, that's your answer. If your limit looks like infinity plus infinity, your answer is infinity. Or if it's negative infinity minus infinity, it's negative infinity, right? If it's 0 to the infinity, the answer is 0. It's just 0. And does that one seem a little odd to you, that bottom one? Does that make sense? Think about if this one ever seems like that one. Sometimes people have a hard time with that because they think, okay, what's the difference between 0 to the infinity? How is it that 0 to the infinity is undefined or is defined, but 0 to the 0 is not? If 0 to the infinity has to be 0, how could 0 to the 0 be something bigger than 0? People often wonder, right? Okay? That's exactly the way it should be, though, if you think about it. Think about this. If I have 0 to the infinity, well, that's something, if it has that form, that'd be like saying the limit of, say, 0.1 to the infinity. What's 0.1 times 0.1? What's 0.1 squared? 0.01. What's 0.1 cubed? 0.001. To the fourth, it's 0.0001. So you see the trend here, right? If we take a number that's less than 1 and we take it to an infinite power, that's going to drive it down to 0, isn't it? Because every time you multiply successively by a number less than 1, whose absolute value is less than 1, it's going to make the product smaller, right? Okay.
How is 0 to 0?
0 to the 0, well, that one is indeterminate, right? 0 to the 0, I mean, that would be, we didn't do a specific example like that, but we could have. Like, what if this one had been, instead of 1 plus x, what if it had just been x to the x, right? As x approaches 0. That, why is it indeterminate?
Anything to the 0
Anything to the 0
power is 1.
power is 1, but you can't use 0 at, what that rule really says is anything other than 0 to the 1 is 0. Any non-zero number to the 0 power is 1. Justifying that one, that's a little tougher. That's a little bit tougher. Yeah. I don't want to take the time to even try to articulate that. It'll make, I promise you, it'll just make sense to you as you work with this stuff more. But it's really hard to explain why that would be the case. It'll just be intuitive to you, though, at some point. Okay, any other questions on this from the assignment on this stuff before we move on? Megan, did you have did that answer your questions, or do you have more questions?
It's not really that I had like questions. It was more that I just didn't really know how to solve it.
Okay.
Two problems, but I can try to figure it out.
Okay, yes.
How is 1 to the infinity determined?
How is 1 to the infinity? Because it's not really 1. It's 1 point something. See what I'm saying? It's not, if it has the form 1 to the infinity, it could be a number, like what if that was 0.999 to the infinity? You see what that's going to do? It's going to make it smaller and smaller every time, right? Right? What if it's a number that was vanishingly, if the difference between 1 was vanishingly small, was in effect, infinitely small, and you take it to an infinite power, which one wins?
Was it just if it's like infinitely slightly bigger, not infinitely, like 1 over infinity more than 1, then it'd be infinity. 1 over infinity less than 1 would be 0.
Okay, then how about this one? What if you had 0.9 repeating with an infinite number of 9s, and you take that to an infinite power? Which one wins? Which one wins? Is it the fact that it's infinitely close to 0? Does that drive it to 1? Or does the fact that you're multiplying it together an infinite number of times drive it to, you know what I mean? It's,
Oh, you mean like 0.0000001?
yeah. I mean, we could
That's 0, though.
we could do it. I mean, if you wanted like 0, you're asking about
Well, that's a 1 to infinity.
1 to the infinity you're asking about. Okay, well, isn't that the one we just did? We just did that one. That was 1 to the infinity, right?
So don't we just need to know if 1 to the x is more than 1, then it'd be infinity?
No, because that is, look, that is more than 1. That's 1 point something, isn't it? We had 1 point something to the infinite power, but the way that we built that infinity and the way we built the 1 point something conspired to give us an answer of E. Yeah. You see, it's just a matter of which is more aggressive. Is the exponent more aggressively multiplying it, or is the number here more aggressively approaching 0, approaching 1? Yeah, it is weird. Yep.
to 1 or 0 to infinity or something like that. Because I remember it was either you saying something about it or I saw a video or something like that.
Say it again. What was it again?
Whether 0, whether 0 and 1 is infinitely bigger.
Oh yeah, we talked about that. Yeah,
Okay.
yeah. So there's a lot going on with infinity. Infinity just isn't. It's not as simple as you probably thought it was about a year ago, right? Or a month ago, right? Okay. So then, all I want to do maybe today is just introduce some vocabulary to you. How much time we got? 13 minutes. Yeah, it's good to just get the concept out there so your brain starts working on it.